Let's take a deep look at the natural response of a resistor-inductor-capacitor circuit. The RLC is representative of real-life circuits we can actually build, since every real circuit has some finite resistance. This circuit has a rich and complex behavior that finds application in many areas of electrical engineering. Using Kirchhoff's law, which states that in any closed loop, the sum of the voltage drop is equal to zero, we will model the RLC circuit using a differential equation. L is the inductance in henries, R is the resistance in ohms, E is the electromotive force in volts, I is the current in amperes, C is capacitance in farad, Q is charge in coulombs. When the switch closes, the current is zero, and the capacitor is charged up to an initial voltage of volts, giving a differential equation in terms of current. This figure are the circuit conditions just after the switch closes, giving us the following equation with a second derivative term, a first derivative term, and a plain I term, all still equal to zero. This is called a homogeneous second-order ordinary differential equation. It is homogeneous because every term is related to I and its derivatives. It is second order because the highest derivative is a second derivative. It is ordinary because there is only one independent variable. Now, we set about solving our differential equation.
One way of expressing an RLC circuit is by using the method of linear differential equation. So we have here the formula for linear differential equation, and this formula is a particular application for circuits. So given by these initial values, we have 3 amperes. For the resultants, we have 50 ohms. For the inductance, we have 0.4 henries. And for the capacitance, we have 10 raised to negative 5. And we have also 3 coulomb charge. So plugging in these values into this formula, we're going to have this 0.4 di over dt plus 50I plus 10 over negative 5 times 3 is equal to 0. Now we have to simplify this. It will be 0.4 di over dt plus 50I is equal to, this one is equivalent to 300,000, and we're gonna move it to the right hand side, so it will be negative now, 300,000, negative 300,000. After that, we're gonna multiply this into 1 over 0.4, 1 over 0.4, so it will be cancelled. So we have the di over dt plus 125I is equal to negative 750,000. After that, we're gonna be using the integrating factor. Now we have mu of t is equal to e raised to, we're gonna raise this one here, so it will be raised to integrating factor of 125 dt, and this will be equal to e raised to 125 t. Solving for the equation of I, because I is the equation for the current, we're gonna have I of t is equal to e raised to 125t multiplied by negative 750,000 plus c all over e raised to 125t. Simplifying this, we're gonna have negative 6,000 e raised to 125t plus c all over e raised to 125t. So our general solution will be I of t is equal to negative 6,000 plus c e raised to negative 125t. So this general equation, we can now use this to input this in our initial values. So we're gonna have at t is equal to 0, we have I is equal to 3 amperes. So we'll have 3 is equal to negative 6,000 plus c e raised to 0. The value of our c will become 6,003. After getting the value of c, we can now input this into the general equation. So we will have a particular solution of I of t is equal to the value of c times e raised to negative 125t minus 6,000. Therefore, this is the equation for the current.
One way of finding an equation that can describe an RLC circuit is by using the method of separation of variables. So in order to find that equation, we use this equation, which is based on Kirchhoff's voltage law, which states that the summation of the voltages across the components connected in series is equal to 0. So in this problem, we have an initial condition of 3 amperes at t is equal to 0. And we input the following given into this equation. So we have an inductance of 0.4 Henry, 50 ohm resistance, and a 1 over 10 to the negative 5 farad capacitance, and a 3 coulomb charge. So we now have this equation. We just need to simplify it. So 0.4 di over dt plus 50i plus, let's calculate. So 1 over 10 raised to negative 5 times 3 is equal to 3,000. 300,000 is equal to 0. So now, since this is separation of variables, so we just leave the term with the di over dt on the left hand side, and we transpose this expression to the right hand side. So 0.4 di over dt is equal to negative 50i minus 300,000. So now we multiply both sides by dt. di is equal to negative 50i minus 300,000. So now we have a dt on the right hand side. So since we're separating the variables, we divide both sides by the coefficients of the differentials before we integrate. So in this side, we divide it by this expression. We have negative 50i minus 300,000 is equal to dt divided by this coefficient 0.4. Now we're able to integrate it since they're on their respective variables in both sides. So this denominator, as observed, it still can be factored out. So we factor it out we factor negative 1 over 50. So inside, so the denominator will be I plus 6,000. So we do this in order for us to not be able to have difficulty in integrating later on. And this remains dt over 0.4. So now we're able to integrate it. So for the left hand side, we have negative 1 over 50 ln I plus 6,000. For the right hand side, we have 1 over 0.4 t plus the constant. So in order to further solve this equation, we need to eliminate the natural logarithm ln by raising both sides by e. Raising both sides by e, yes. So e raised to negative 1 over 50 ln I plus 6,000 is equal to e raised to 1 over 0.4 t plus c. So this will become I plus 6,000 raised to by the law of natural logarithm. So its coefficient will be its exponent. Negative 1 over 50 is equal to e raised to 1 over 0.4 t times e raised to c. Since it's an arbitrary constant, we just consider it as c. Okay. Then, in order to isolate the I on the left hand side and get the explicit form of the general solution, we raise both sides by negative 50. So we raise the left hand side by negative 50. So the left hand side will become I plus 6,000 raised to 1. So it's as is. And the right hand side will be so 1 over 0.4 raised to 50, so times 50 is 125. So e raised to, the negative sign, I forget. So it's gonna be negative 125 t times the constant c. So we just put it here. Okay. Then we transpose 6,000 to the right hand side in order to isolate the I. So c is raised to negative 125t minus 6,000. So now we have our general solution. So this is the general solution. And we'll apply our given initial values. The initial value given is at t is equal to 0, we have 3 amperes. So let us put it here. At t is equal to 0, our I is equal to 3 amperes. So we apply this initial condition into the general solution. So now we substitute I is equal to 3 is equal to c e raised to negative 125 times 0 is 0. So e raised to 0 minus 6,000. So c times e is raised to 0. E raised to 0 is 1 times c. So we have c minus 6,000. And we solve for the value of c is equal to 3 plus 6,000, 6,003. Now we found the value of c. We can now substitute this into the general solution in order to find the particular solution. So in this problem, the particular solution will be the equation that describes the RLC circuit in this problem. So substituting c to the general solution, we now have I as a function of time is equal to 6003, substituting this equation, 6003 e raised to negative 125t minus 6000. So now we've already found the equation that describes this RLC circuit by using the method of separation of variables. So the dependent variable here is the current I. But if you want your dependent variable to be in terms of charge into QT, you just have to integrate this equation. But for now, this is our equation. So that's how you use the method of separation of variables in solving for an equation, in finding an equation that describes the RLC circuit with the given initial condition. That's all.
Problem, we are given a charge C which has a 1.0 times 10 is to negative 6 farads, a resistance of 4 times 10 raised to 2 ohms, or 400 ohms, and an inductor of 0.3 henries. We are asked to find the charge at time t, with conditions that the initial charge at time 0 is equal to 1.0 times 10 raised to negative 6 coulombs, and a current at time 0 which is equal to 0, or Q prime of 0. Next, we are asked to find the charge Q at time is equal to 5. Now, what we're gonna use in this problem is a differential equation related with the RLC circuit. Now, the differential equation that we are going to use is given by L times Q double prime plus R Q prime plus 1 over C Q is equal to 0. Now, solving this differential equation is very easy since all of these givens are constants. So there is no need to use variation of parameters or any of such, and we just gotta need to plug in all of these values. So plugging in, we have 0.3 Q double prime plus 400 Q prime plus 1 over 1.0 times 10 raised to negative 6 Q is equal to 0. So we need to simplify this by dividing all of this equation into 0.3, canceling this out, and simplifying this expression. So we have our differential equation, which is Q double prime plus 400 over 0.3 Q prime plus, raising this, we have 1.0 times 10 raised to 6 all over 0.3 Q is equal to 0. So now we have our differential equation. So we are given this differential equation, and we need to find the general solution at time t. So how do we find it? First, we're gonna use homogeneous of higher order differential equation. So in solving this type of differential equation, we need to find the characteristic equation. Characteristic equation. Which is r squared plus 400 all over 0.3 r plus 1.0 times 10 raised to 6 over 0.3 equals to 0. Notice that the degree of this characteristic equation responds to the degree of the differential equation, given that q prime is r squared, q double prime is r squared, q prime is r, and q is a constant of 1. So in solving this, we need to use calculator. It cannot be solved manually, or it is a tedious process to solve. So we gotta go set up, and we use polynomial with degree of 2. So we plug in our values. We have 1, 400 over 3, 0.3, and 1.0 times 10 raised to 6 over 0.3. So we are given that our roots, r sub 1 is equals to negative 2000 over 3 plus 1699.67 I, and the other root is given by negative 2000 over 3 minus 1699.67 I. Notice that our roots are complex. So in this type of roots, our A will be negative 2000 over 3, and our B will be 1699.67. This is case 3 of the higher order homogeneous differential equation. So our general solution is given by q of t is equals to a constant of c1 e raised to at cosine b times t plus c2 e raised to at sine b of t. So plugging in all of our values, we now have c1 e raised to negative 2000 over 3t cosine 1699.67 t plus c2 e raised to negative 2000 over 3t sine 1699.67 t. So this will be our general solution. However, we need to find the constant c1 and c2 with the given initial conditions before, which is q sub o, q or q prime, q of 0 is equals to 1.0 times 10 raised to negative 6 coulombs, and q primes of 0 is equal to 0. So given this general solution with unknown constants c1 and c2, we will be finding these values with the given initial conditions, which is q of 0 is equals to 1.0 times 10 raised to negative 6. So given this general solution with unknown constants c1 and c2, we will be finding this with our given initial conditions, which is q of 0, the initial charge, is equal to 1.0 times 10 raised to negative 6 coulombs. And since we know that there is no current, and this current is equated to q prime of 0, then it is equal to 0. So finding this, we just need to plug in these values to our general solution to find our particular solution and solve for the constant c1 and c2. So given that our q, whereas the t is equal to 0, we have C1 e raised to negative 2000 over 3 times 0 cosine 1699.67 times 0 plus C2 e raised to negative 2000 all over 3 times 0 sine 1699.67 times 0. So we know that e raised to 0 is just equal to 1, and cosine is just equal to 1. Sine of 0 is equal to 0, and e raised to 0 is equal to 1. So we need to find C1 here, since C2 is already cancelled out. So now we have 1.0 times 10 raised to negative 6 is equal to C1. This will be our first equation. Now we have to solve the constant 1. We will try to solve C2 by differentiating this general solution, since we are given q prime of 0 is equal to 0. Now, differentiating this, we now have q prime of t is equal to C1. Then we'll apply the product rule, which is e raised to negative 2000 over 3. Copy this one, differentiate this one, so we have times negative negative 1699.67 sine 1699.67 t plus copy this one, so we have cosine 1699.67 t times, differentiating this, we have negative 2000 all over 3 e raised to negative 2000 all over 3 t. So we're done with this. Next, we need to differentiate this one, so we have C2 times, apply product rule, we have copy the first term, we have e raised to negative 2000 all over 3 t. Then differentiate this one, we have times 1699.67 and cosine 1699.67 t plus, we need to copy this one, so we have sine 1699.67 t times negative 2000 over 3 e raised to negative 2000 over 3 t. So by continuing in solving this, we will be having q prime of 0, which then equates all of this, the t values in this equation, into 0. We know that C1 is 1.0 times 10 raised to negative 6. Then e raised to 0 is 1. Since the t here is 0, then this cancels out. But this will be 1. Times negative 1699.67 sine, since there is a t here and sine of 0 is 0, so this whole term will be cancelled out. Plus, we know that cosine 1699.67 times 0 is cosine of 0 is equal to 1, so we will be having 1 times this term, since e raised to this having a t value of 0, and we will be having a value of 1, since e raised to 0 is 1, so we have negative 2000 all over 3. Then plus our C2 here, having this will be cancelled to 1, and cosine of 0 is 1 times this one, so we will be left with 1699.67 plus sine of 0, sine of 1699.67t, which t is equal to 0, this whole term will be cancelled out, so this will be 0. We know that q prime of O is 0, and this distributing this one, we will be having 1.0 times 10 is to negative 6 times negative 2000 over 3 plus 1699.67 C2. Now using our calculator, we can solve for this. 1.0 times 10 raised to negative 6 times negative 2000 over 3. We have negative 1 over 1500 plus 1699.67 C2 equal to 0. So we will be having 1 over 1500 equals to 1699.67 C2, whereas C2, our C2 will be 1 over 15 times 1699.67. We have 3.922 times 10 raised to negative 7. So our general solution with unknown constants is equal to C1 e negative 2000 all over 3 t cosine 1699.67 t plus C2 e raised to negative 2000 all over 3 t sine 1699.67 t. Based on our computation earlier, our C1 is given by 1.0 times 10 is to negative 6, and our C2 is equals to 3.922 times 10 is to negative 7. So plugging this in, we now have our particular solution for the charge at time t is equal to 1.0 times 10 is to negative 6 e raised to negative 2000 over 3 t cosine 1699.67 t plus 3.922 times 10 is to negative 7 e raised to negative 2000 over 3 t sine 1699.67 t. So this will be our answer. So solving for t, time is equals to 5, we now have our charge will then be equal to 0. This implies that after 5 seconds, there is already no charge. But suppose that our t is less than 1 second but greater than 0, we would have a charge. Suppose that we have a time t is equals to 0.006, then what will be our charge at time 0.006? 0.006. Our charge will be negative 1.812 times 10 raised to negative 8. This implies that the lesser the time, or that the minimal the value of it, there will be a charge occurring at this kind of equation.